Okay, so we are going to finish our discussion of gases in the ocean by talking a bit more about oxygen, specifically where it came from and where we lose oxygen in the ocean. And in the background here, I have a few different ways that we measure oxygen in the oceans. In the upper left here, those bottles are Niskin bottles. Those are used to take oxygen measurements in the ocean, or take water samples in the ocean, and we can measure that oxygen using titrator setups like we have in the lower left. That historically has been how we measure all the oxygen in the ocean. But more recently, we have a lot more autonomous vehicles like the profiling floats right above me that measure oxygen throughout the water column and send data back via satellite. So we're really starting to change the way that we sample the ocean and how much detail we can get. So here are some plots showing oxygen in the ocean today. So in the upper left, that's the surface oxygen concentration, and darker colors represent lower oxygen. Lighter colors, the yellows and getting close to white, represents higher oxygen concentrations. And so we see the same pattern as sea surface temperatures, basically, which is that in the colder areas to the north and the south, we have more oxygen, and warmer areas around the equator we have less oxygen. And so if you remember what we learned about solubility, cold water holds more gas, warm water holds less gas. And so that's our friend solubility coming back again. That really, the temperature controls the main oxygen distribution throughout the globe at the surface. We see that in the lower left-hand plot. This is the departure from oxygen saturation. So 0% basically means that the water is holding exactly as much oxygen as it can. And you see slight positive saturation throughout. That's mainly from biological production. A few areas where it's lower. That's upwelling of deep waters that are low in oxygen. But basically, the water at the surface is pretty close to holding the amount of oxygen that it can based on solubility. The picture gets different once you go into the ocean interior. So in the upper right in B, we have an interior plot of oxygen at 525 meters. And now you start to see some very low values. The surface values were in the sort of 240 to 360 micromoles per kilogram range. In the interior, we're getting down now into less than 60 micromoles per kilogram, in places much less than that, in fact. And we'll talk some about why those patterns of low oxygen values look the way they do. Panel D there is a cross section, so this is as though we're sort of inside the ocean looking sideways, and the North Pole, 90 degrees north, is to our right, South Pole, 90 degrees south, is to our left, and we're looking at 5 kilometers of the water column. And there we see that you get those very high oxygen values right near the surface, but then not too far below you get much lower oxygen, and then as you get deeper it gets higher again. So why is oxygen lower at depth? We'll talk about that. And the main reason, and we'll go over this a few different times today, but the main reason is that at the surface of the ocean you have photosynthesis, where you take carbon dioxide and water and you make organic matter. CH2O is our general formula for organic matter, and produce oxygen, right? So you're producing oxygen at the surface. A lot of that escapes out into the atmosphere. Some of it mixes into the ocean interior, but mostly that stays in the surface. Now that organic matter, some of it, your phytoplankton, your zooplankton, whales, they live, but then they die and they sink out. And as they sink out, that organic matter is broken down through respiration. Respiration breaks down organic matter and consumes oxygen, so that lowers your oxygen in the ocean interior. And so that gives you the lower oxygen at depth. It doesn't tell you exactly why we see these patterns, and we'll get more into that later, but that's the basic structure of oxygen, is that you have high values controlled by the atmospheric partial pressure of oxygen at the surface, and lower values at depth due to respiration of sinking organic matter. Okay, so we can show this in a sort of very box model schematic here, where we have 4 boxes: an atmosphere box, surface ocean, a high latitude surface ocean, and a biological pump. And so this high latitude surface ocean is again meant to represent those high latitude areas where you get deep mixing and you can connect the surface ocean to the deep ocean. So they operate a bit differently than those big, large, sort of tropical, subtropical areas in the surface ocean. But what's going on in these different boxes? Well, in those upper surface boxes, we have photosynthesis, we're producing oxygen, and then you have respiration, consumption of oxygen at depth. And that's due to that biological carbon pump that we've talked about a few times now, where you have biological production at the surface ocean. Some of that sinks out and is respired, and so that's consuming oxygen. And so that sets up this gradient of oxygen that we see throughout the ocean. And there again, this is bringing that section, the cross-section plot again, and we see those low oxygen values near the surface, but at depth. Now, why do we not see the lowest oxygen all the way in the deep ocean? Well, that's in large part because of those high latitude ocean boxes, that you can connect the deepest parts of the ocean to these very cold, high solubility regions in the ocean. And so you're bringing deep, high oxygen waters all the way into ocean interior. And that's not necessarily where you have the most organic matter respiration. Most of the organic matter is respired in, say, the upper kilometer or so of the ocean. So you get the lowest oxygen values nearer to the surface, and then you have oxygen increasing again as you get down into the waters that are a bit better ventilated, even if they are deeper down. Now, oxygen has not always been present in the ocean. If you go back to the origination of the Earth, there's very little oxygen present in the atmosphere. There's still some, just due to breakdown of atmospheric molecules, but there is very, very little. So this plot here is showing a sort of conceptual plot of oxygen evolving over time. On the left-hand y-axis is the partial pressure of oxygen, but it's on a log scale, so small changes make a big, big difference, right? We're talking 5, 6, 7 orders of magnitude across that scale. And then on the right-hand axis, it's the same values, but this time represented as the present atmospheric level. So 1 being present atmospheric level, and then the numbers below 1 are the fraction of current atmospheric oxygen. So basically it's saying at 0 years ago, that's today, that's present day, that's when we've had the most oxygen present in the ocean over time, and also in the atmosphere. So going back to that very low oxygen concentrations or partial pressures 2.5 to 4 billion years ago, that started to change as oxygenic photosynthesis developed. So as you started to develop oxygen production through photosynthesis, where you're forming organic matter and producing oxygen, eventually that led to what's known as the Great Oxygenation Event, where you suddenly had a lot more oxygen present in the atmosphere and in parts of the ocean. The ocean wasn't uniformly oxygenated, and you still had regions with very little or no oxygen. And that's in part because while photosynthesis can produce organic matter and oxygen, once that organic matter is consumed, then you're also removing the oxygen that was produced. And so it wasn't until you had the rise of vascular plants on land, basically big plants on land, where not all of the organic matter was respired quickly, where you could have very little of organic matter, that you got that second, or really there's been a lot more than just 2 jumps in oxygen, but where, in this very simple schematic, that next jump in oxygenation, and you get close to present atmospheric levels of oxygen, right? So you have oxygen that's produced through photosynthesis, and but instead of the plants immediately breaking down, as you had these bigger vascular plants that were formed, then that organic matter could be buried and removed from contact with the atmosphere, and that oxygen that was produced during photosynthesis would stick around, and so your oxygen would increase over time. Now, if we go and take a look at how photosynthesis and chlorophyll look in the ocean today, we can look at this map or this movie based on satellite measured chlorophyll, and they're not measuring chlorophyll exactly, it's measuring ocean color, and they're using those ocean color measurements to calculate chlorophyll concentrations in the surface ocean. You can see the dates moving through in the bottom left there. So now we're in 2011, getting to 2012. So January, February, that's getting spring and summer in the northern hemisphere. You see greening in the northern hemisphere, and then as you get into the winter months, northern hemisphere winter months, in October, November, December, that's when you see the greening in the southern hemisphere. So there's a seesaw, but consistent areas of high production in the north and south subarctic, subpolar regions, and in the equatorial regions. You also have consistently high production, and then very low production, very low chlorophyll in the open ocean gyres, where you see those blue shapes. And so how does this impact oxygen in the ocean? Well, in addition to surface production, we also have to consider water age. And what I mean by water age is how long has it been since water was last exposed to the atmosphere. So this paper is based on carbon isotopes, where they have on the far left here is showing the mean age derived from interior ocean measurements of carbon isotopes, and the blue colors are younger water, so water that was more recently in contact with the atmosphere. Red are older waters. And so where we see those dark blues, the youngest waters, those are our areas of deep water formation that we've talked about now a few times. So this is North Atlantic and in the Southern Ocean around Antarctica. As you get into the Pacific, you start getting into the darker reds, much older water. You can look at the Atlantic mean age, so this is a cross-section looking at the Atlantic, or Pacific mean age, a cross-section looking at the Pacific, and we see this general trend of younger water in the Atlantic and older water as you move into the Pacific, with the oldest waters being in the North Pacific, where you get up to waters that have been out of contact with the atmosphere for around 1,400 years or so. And so why does that matter? Well, if we look at our maps of oxygen minima throughout the ocean, we see that Pacific has the oldest, or has the lowest oxygen. So in the upper plot, this is the oxygen at the oxygen minimum, essentially saying we have oxygen minima throughout the ocean, but what is the oxygen concentration at its lowest in the water column? And where you see the lowest oxygen is in the Pacific. Some areas also in the Atlantic and Indian, where you get into those low blues, but basically the Pacific, you see the lowest, especially along the eastern tropical Pacific. Another way to look at oxygen minima or low oxygen values is to look at, say, just the depth where you have one particular low oxygen value. So in this case, they're looking at where you have 60 micromoles per liter oxygen. If you recall, surface oxygen values were in the 250 to 400 micromoles per kilogram, so this is getting down pretty low. And in Pacific, this is where you have low oxygen values relatively close to the surface. So that eastern tropical Pacific, getting into less than 200 meters of water. Same with northern Indian Ocean, and a little bit, not much, but a little bit in the Atlantic. And so if we take our maps of where we have chlorophyll, which we can kind of say is roughly equivalent to where we have lots of organic matter production, and we also look at our mean age in the ocean, we see that then when we get the oxygen minima in there, the oldest water, where you have a lot of biological production, is where you see the lowest oxygen water. And so the low oxygen in the water it's not just due to local biological production. So it's not just saying, well, you've got high production above in the surface here, and so you've got low oxygen in the water column. It's also because that water, it's so old, it's been circulating through the ocean, and it's accumulating that respired oxygen signal. So you have organic matter sinking out, even if it's tiny amounts. If you get water that's 1,000 years old, those tiny amounts add up, and a lot of the oxygen has been consumed in the water. Now we see oxygen minimum zones. The biggest oxygen minimum zones, this is a map showing the dissolved oxygen content at a given isopycnol. This is 27.05. It's sort of like the densest waters that are still seasonally exposed in the ocean. The lines on here, those black contour lines, we've got one at 60 micromoles per kilogram, one at 5 micromoles per kilogram. So these show that the biggest oxygen minimum zones in the world are in this eastern tropical Pacific. And so that's in part due to high production off the coast of North and South America there, and then also poor ventilation, right? It's these waters have taken a long time to get there. There's no local source of well-ventilated waters. There's no place where you have newly exposed waters that are coming down to these regions. And so over time, that signal accumulates and accumulates and accumulates, and you get very low or anoxic waters that develop over these very large areas. So we call these oxygen minimum zones. They're also called oxygen deficient zones because technically there are oxygen minima everywhere in the ocean. So oxygen deficient implies that there's actually not enough oxygen for things to live and grow and thrive. And one thing that's happening is that these zones seem to be expanding. And there's a few reasons for that. One, the oceans are warming, and as they warm, again, due to solubility, the water can hold less oxygen. And so just everywhere in the ocean, but especially in areas that are low in oxygen, that starts to matter, and you start to lose more oxygen, and so that can cause expansion of OMZs. You also have increased stratification. You'll learn more about the temperature effects on density in physical oceanography later this semester, but essentially warming water makes that lighter, it makes it less dense, and that makes it harder for water to mix down. And so you restrict, you reduce the ventilation of water that occurs in the winter when things are cooling and mixing down deep. And so that reduced ventilation, the increase in stratification, keeps oxygen from going into the water as well. And then there are also temperature effects on respiration, and generally organisms tend to use more oxygen when it's a little bit warmer. And so basically those three things combined starts to expand our OMZs, and that can be really important for, say, fisheries in the Pacific that feed an awful lot of people, and this starts to threaten habitat, restrict fish to smaller regions, and also starts to change ocean biogeochemistry. So just to summarize, we've got a few key points here. One, oxygen gradients in the ocean are determined by a combination of your atmospheric partial pressure, photosynthesis in the surface ocean, and respiration at depth. Our ocean oxygen has gone through very large changes in the past, so our current well-oxygenated ocean has only been around for the last 400 million years or so, really since the rise of vascular plants on land. And our oxygen minimum or deficient zones develop with a combination of high biological production, poor ventilation, and the extent of these OMZs is predicted to increase in the future due to warming and stratification and increases in respiration. So that it concludes our gases and seawater section of this module. I hope you enjoyed it, and if you have any questions, feel free to reach out.